Hello there, and welcome to Cosmos for Sleep. Tonight, we're embarking on a serene journey through the fascinating realm of interstellar travel. If these calm, curious explorations help you unwind, consider liking and subscribing to the channel. It helps others find their way here too. For now, just breathe, let your eyes grow heavy, and let's begin. Even the nearest star beyond our Sun, Proxima Centauri, is over 4 light-years away, meaning its light takes more than 4 years to reach us. This immense distance highlights the primary challenge of interstellar travel. The sheer scale of space, a boundless, tranquil ocean, means that even our closest celestial neighbors reside at distances that defy casual comprehension. A single light-year, representing the distance light travels in 1 Earth year, is an unfathomable 6 trillion miles, or 10 trillion kilometers. When we speak of 4 light-years, we are contemplating a void so vast that our most powerful conventional rockets would take tens of thousands of years to traverse it. This cosmic expanse sets a patient, fundamental constraint on any aspirations of journeying to other stars, demanding ingenuity and profound temporal commitment from humanity. The gentle glimmer of a star in the night sky, though appearing close, is in reality an ancient beacon, its light having traveled for years, silently bridging an immense, silent chasm. This grand scale necessitates not just faster vessels, but entirely new ways of conceiving travel across the universe's placid, stretching canvas. Our own modest forays into the cosmos vividly illustrate this monumental challenge. Consider our fastest human-made object, the Voyager 1 spacecraft. This pioneering vessel, launched in the 1970s, travels at a remarkable, unhurried speed of approximately 17 kilometers per second, or about 38,000 miles per hour relative to the Sun. Yet, even at this astonishing velocity, a testament to human engineering and patience, it would still require approximately 73,000 years to reach Proxima Centauri. This illustrates the truly vast gulfs of space that separate even closely situated stars. The journey would unfold over a timescale far exceeding recorded human history, transforming what might seem like a swift voyage in a science fiction tale into an enduring, multi-generational endeavor in reality. The patient, measured pace of Voyager 1's silent drift through the deep, cold reaches of space serves as a profound reminder of the immense, serene distances that must be gracefully overcome to touch another star. Such a slow, deliberate passage emphasizes the need for revolutionary advancements in propulsion. To overcome such immense timescales, scientists contemplate methods of achieving speeds that are a substantial fraction of light's own serene velocity. Should a traveler manage to move at speeds very close to that of light, a fascinating and profound phenomenon known as time dilation would subtly alter their experience of time. According to Albert Einstein's profound theory of relativity, time would pass distinctly more slowly for those aboard the swiftly moving vessel compared to those who remain stationary on Earth. This means a journey that might subjectively feel relatively brief. Perhaps a few decades of active travel and exploration to the interstellar Voyager could in reality span many centuries or even millennia for their loved ones and civilization back home. It is a delicate dance with the very fabric of space-time itself, offering a curious, almost paradoxical solution to the brevity of a single human life in the face of cosmic distances. The explorer would return to a vastly changed world, a silent testament to the universe's patient unfolding, raising deep questions about the nature of connection across epochs. However, accelerating any spacecraft, even one of modest size, to such extraordinary, near-light velocities demands an almost unimaginable amount of energy. The physics involved dictate that as an object approaches the speed of light, its effective mass increases, requiring exponentially more energy for further acceleration. The energy needed to propel a vessel to a substantial fraction of light speed could potentially be equivalent to the entire global energy consumption of Earth for many, many years, perhaps even centuries, if not millennia. This monumental undertaking presents a significant engineering hurdle. pushing the boundaries of what is currently achievable with our technology. Developing propulsion systems capable of delivering such immense and sustained power, perhaps through advanced nuclear fusion or even more exotic means like antimatter annihilation, remains a central quest in the dream of interstellar exploration, requiring breakthroughs in fundamental physics and engineering that currently lie beyond our grasp. The sheer, colossal scale of this energy demand underscores the profound difficulty inherent in achieving truly swift cosmic voyages, demanding entirely new power sources. As a vessel embarks on such a profound journey, it would traverse the interstellar vacuum. This space between stars is not entirely empty, but rather an incredibly dilute medium, a vast, hushed expanse containing only about 1 atom per cubic centimeter on average. This sparse mixture consists primarily of hydrogen and helium atoms, along with traces of dust and pervasive magnetic fields. While this environment seems almost perfectly empty, a truly deep vacuum, this thin mixture of gas and dust still presents subtle yet critical challenges for high-speed travel. At relativistic velocities, even these sparse microscopic particles could become miniature projectiles, striking the spacecraft with potentially destructive force. This is the interstellar dust collision hazard. Even microscopic dust grains, though sparse, become lethal projectiles at relativistic speeds, posing a significant threat to the integrity of a spacecraft. Imagine a grain of sand hitting a vessel at a fraction of light speed. The impact energy would be enormous, capable of causing substantial damage or even catastrophic failure. To mitigate this pervasive, subtle danger, advanced shielding and sophisticated navigation systems would be absolutely critical, allowing a craft to either deflect or gracefully avoid these tiny, high-velocity cosmic particles. The design of such a shield would need to be revolutionary, perhaps incorporating layers of self-healing materials or even electromagnetic fields to sweep away incoming debris. This silent rain of particles, though imperceptible in the vastness, presents a constant, delicate challenge to the quest for swift interstellar travel, reminding us that even emptiness holds its own quiet perils. Navigating this fine cosmic dust requires a blend of robust protection and elegant avoidance, ensuring a peaceful passage through the ethereal medium. One elegant solution to the challenge of propulsion, especially for unhurried journeys, lies in the concept of solar sails. These are vast, thin, expansive membranes, often made of highly reflective material, designed to use the gentle, persistent pressure of sunlight to propel a spacecraft. Much like a sailboat on an ocean, a solar sail catches the momentum from photons streaming from a star. While they are inherently slow to accelerate, gaining speed gradually over months and years, they require absolutely no propellant once deployed. This absence of onboard fuel allows for lighter spacecraft and enables them to achieve remarkably high speeds over very long durations, accumulating velocity steadily as they drift through the cosmos. The subtle push of starlight, a constant, pervasive force, could thus guide a vessel on a patient, millennia-long journey, a testament to the quiet power of light itself. It is a tranquil, fuel-efficient method, perfectly suited for the unhurried pace of the universe. Building upon the solar sail concept, an even more ambitious idea emerges: laser sails for faster travel. This advanced propulsion method envisions utilizing powerful ground-based or orbital lasers to push specially designed light sails. Instead of relying on the diffuse light from our sun, these immense laser arrays would direct concentrated beams of light onto the sail, imparting a much greater, more immediate thrust. This focused energy could potentially accelerate spacecraft to a substantial fraction of light speed much faster than traditional solar sails, significantly reducing travel times to other star systems. The technological demands are immense, requiring lasers of unprecedented power and colossal mirrors in space to focus these beams with pinpoint accuracy over astronomical distances. Yet, the promise of rapidly propelling small probes to distant stars within decades, rather than millennia, makes laser sails a captivating vision for the future of interstellar exploration, offering a swift, elegant push from our home system into the wider galaxy. For truly rapid interstellar journeys, the quest for the ultimate fuel efficiency leads to antimatter propulsion. This theoretical system involves the controlled annihilation of matter and antimatter, a process that converts nearly 100% of their combined mass into pure energy, as described by Einstein's famous equation E equals mc squared. This offers by far the most efficient known form of propulsion, vastly outperforming chemical or even nuclear fission rockets. The challenge, however, is immense. Producing and storing sufficient quantities of antimatter, which instantly annihilates upon contact with ordinary matter, is currently far beyond our technological capabilities. It requires colossal amounts of energy to create even tiny amounts of antimatter, and safely containing it for transport presents an extraordinary engineering puzzle. Despite these hurdles, the sheer energy density of antimatter makes it a tantalizing, albeit distant, prospect for propelling future starships at truly impressive velocities, offering a pathway to bridge the cosmic gulfs with unprecedented speed. In the mid-20th century, a bold and powerful concept for interstellar travel emerged from the shadows of the Cold War: nuclear fission rockets, specifically Project Orion. This ambitious design proposed propelling a massive spacecraft by detonating small, controlled nuclear bombs behind it. Each explosion would impart a powerful pulse of momentum to a large pusher plate at the rear of the vessel, pushing it forward. While this method promised immense thrust and the potential to reach high speeds, far beyond anything conventional rockets could achieve, it also raised significant environmental and safety concerns due to the radioactive fallout from the repeated nuclear detonations. The audacity of the concept was remarkable, envisioning a true spaceship of colossal scale, but the practical and ethical implications ultimately led to its shelving. Project Orion remains a fascinating, if controversial, historical footnote in the quest for interstellar propulsion, a testament to humanity's early, powerful imaginings of star travel. Looking further into the future, the concept of nuclear fusion for sustained thrust holds immense promise. This propulsion method would harness controlled nuclear fusion, the very process that patiently powers our sun and all other stars across the cosmos. By fusing light atomic nuclei, typically isotopes of hydrogen, into heavier ones, an enormous amount of energy is released. If we could control this process safely and efficiently in a reactor, it could provide sustained, powerful propulsion for interstellar missions, offering far greater efficiency and a cleaner energy source than nuclear fission. The fuel, hydrogen isotopes, is relatively abundant in the universe, meaning a fusion-powered starship could theoretically carry enough fuel for extensive voyages without the need for constant resupply. Achieving controlled fusion on Earth for energy generation is already a monumental scientific and engineering challenge, but its successful application to rocket propulsion could unlock the door to genuine interstellar travel, allowing for a more patient, yet powerful, journey through the stars. As a spacecraft journeys at a substantial fraction of light speed, the universe's appearance would subtly yet profoundly transform due to relativistic optical effects. Stars and galaxies directly ahead of the vessel would appear to shift towards the blue end of the electromagnetic spectrum, a phenomenon known as blue shift, as the light waves are compressed by the craft's motion. Conversely, stars and galaxies behind the vessel would appear red-shifted, their light waves stretched as they recede. Furthermore, the entire field of view would appear to contract, with stars seemingly congregating towards a central point directly ahead of the craft, while the rest of the sky would appear darkened. This distortion of the cosmic canvas, a visual manifestation of Einstein's theories, would be a breathtaking and disorienting experience for any traveler, transforming the familiar constellations into streaks of light. It is a quiet, ethereal dance of light and speed, a reminder of the profound changes that occur when one truly approaches the cosmic speed limit. Before even reaching the vast, open expanse of interstellar space. Any outbound mission from Earth must first traverse our own solar system's immense, ethereal boundary. This outermost region is known as the Oort cloud, a vast, spherical shell of billions of icy objects that gently encircles our Sun at distances extending up to 1 light-year away. Traversing even this initial boundary, this distant, silent reservoir of primordial ice and rock would demand thousands of years with current propulsion technology. It is a slow, patient journey through a sparse, cold frontier, a testament to the immense scale of our own home system. The Oort cloud acts as a cosmic prelude, a long, quiet passage that must be navigated before the true interstellar void is entered. Its silent, distant presence reminds us of the profound distances that must be overcome, even before we truly leave our stellar neighborhood behind. The journey through this icy realm is a gentle, unhurried drift towards the deeper cosmos. Despite the monumental challenges, the motivation for interstellar travel has been profoundly bolstered by the recent discovery of thousands of exoplanets. These distant worlds, orbiting stars far beyond our Sun, have transformed the idea of other planetary homes from pure speculation into a tangible, inspiring reality. The sheer abundance of these exoplanets, some of which reside within their stars' habitable zones where conditions might allow for liquid water and potentially life, has made the concept of interstellar destinations far more concrete and deeply inspiring. Each new discovery fuels the human imagination, painting a picture of countless worlds awaiting discovery, offering a silent invitation to explore beyond our familiar solar system. The serene, distant glow of these other suns, each potentially cradling its own family of planets, serves as a quiet, persistent beacon, drawing our gaze outward and reinforcing the enduring dream of one day reaching their distant shores. Among these myriad exoplanets, Proxima Centauri b holds a particular allure. This fascinating world orbits our nearest stellar neighbor, Proxima Centauri, a small, quiet red dwarf star located just over 4 light-years away. What makes Proxima Centauri b especially intriguing is its position within its star's habitable zone, meaning that conditions on its surface could potentially allow for the presence of liquid water, a fundamental ingredient for life as we know it. While much remains unknown about this distant world, its proximity and potential habitability make it a prime candidate for future interstellar exploration. It represents a tangible, nearby target, a beacon of possibility that could one day host humanity's first direct robotic or even crewed mission to another star system. The gentle, persistent whisper of its potential for life makes Proxima Centauri b a compelling, silent invitation for humanity to reach out beyond its cosmic cradle, inspiring the quiet, determined pursuit of interstellar dreams. As humanity contemplates these profound journeys, the practicalities of communication across such immense distances become a central consideration. Due to the finite speed of light, messages sent between Earth and an interstellar probe would experience significant delays, taking years to travel just one way. This means that real-time communication, as we understand it, would be utterly impossible. A simple query from Earth might take 4 years to reach a probe at Proxima Centauri, and its response another 4 years to return. This 8-year round trip creates a profound sense of cosmic isolation for the crew, if human, or demands extreme autonomy from robotic explorers. Such delays necessitate a patient, long-term approach to mission control, where decisions must be made far in advance, and the spacecraft must operate largely independently. It is a silent, unhurried dialogue with the distant reaches of space, where time itself stretches between every whispered word. This fundamental limitation shapes the very architecture of interstellar missions, emphasizing self-reliance and foresight. For long-duration interstellar missions carrying human crews, ensuring the health and well-being of the voyagers is paramount. Prolonged exposure to weightlessness, while seemingly serene, has significant negative health effects on the human body, including muscle atrophy, bone density loss, and cardiovascular deconditioning. To mitigate these subtle yet pervasive challenges, artificial gravity for crew health would likely be a fundamental requirement. This could be achieved through the slow, steady rotation of a large spacecraft, using centrifugal force to simulate a gravitational pull. Such a rotating habitat would provide a stable, familiar environment, allowing crews to maintain their physical health and comfort over journeys spanning decades or even centuries. The gentle, consistent pull of artificial gravity would offer a sense of normalcy amidst the profound strangeness of deep space, a quiet anchor for the human body and spirit on its long, patient voyage to another star. Furthermore, for these multi-generational or incredibly long voyages, dependence on resupply from Earth is simply not feasible. Therefore, closed-loop ecosystems would be absolutely essential for generation ships or any long-term interstellar habitats. These self-sustaining systems would meticulously recycle all resources, providing a continuous supply of food, water, and breathable air for centuries without external replenishment. Waste products would be carefully processed and converted back into usable materials, mimicking the delicate balance of Earth's own biosphere, but on a much smaller, enclosed scale. This intricate biological and technological dance would require a profound understanding of ecological principles and robust engineering to maintain stability over immense periods of time. Such a self-contained world, drifting silently through the cosmos, would be a testament to human ingenuity and our capacity to create miniature living planets within the vast, tranquil emptiness of space, ensuring the quiet persistence of life on its slow, deliberate journey. As humanity contemplates its own potential for interstellar travel, a profound question often arises: the Fermi paradox. This paradox asks why, if interstellar travel is indeed possible, and the universe is teeming with countless stars and potentially habitable planets, we have yet to find any conclusive evidence of alien civilizations. The great silence of the cosmos, the apparent absence of observable extraterrestrial intelligence, deeply influences scientific and philosophical discourse surrounding interstellar travel. Does it imply that interstellar travel is far more difficult than we imagine, or that advanced civilizations are incredibly rare, or perhaps that they choose to remain silent? This quiet cosmic mystery serves as a sobering counterpoint to our dreams of exploration, prompting deeper reflection on the challenges and implications of venturing beyond our solar system. The Fermi paradox quietly challenges our assumptions, urging a patient re-evaluation of our place in the universe and the potential pathways for life's journey across the stars. Despite these grand challenges, innovative concepts are continuously being developed. The Breakthrough Starshot Initiative, for example, proposes a revolutionary approach to interstellar travel. This ambitious project envisions sending tiny laser-driven probes, each weighing only grams, to the Alpha Centauri system. These nanocraft would be propelled by powerful ground-based lasers pushing immense light sails, with the goal of accelerating them to an astonishing 20% of the speed of light. At this incredible velocity, these miniature vessels could potentially reach Alpha Centauri within mere decades, rather than millennia, offering a glimpse of another star system within a human lifetime. The project represents a bold leap in engineering and propulsion, pushing the boundaries of miniaturization and energy transfer. It is a testament to the persistent human drive to explore, a quiet, hopeful whisper of a future where we can reach out and touch another star, even if only with our smallest, swiftest messengers. Navigating accurately across the immense, silent stretches of light-year distances presents an extraordinary challenge, demanding extraordinary precision interstellar navigation. Even tiny errors in trajectory, seemingly insignificant over short distances, would amplify over the vast cosmic gulfs, potentially leading to a spacecraft missing its target star system by millions of miles or even light years. The gravitational influences of countless stars, gas clouds, and even dark matter must be meticulously accounted for, and the craft's path constantly refined. This requires incredibly sophisticated autonomous navigation systems capable of making minute adjustments over decades or centuries, ensuring the vessel stays on its precise, patient course. The quiet, elegant mathematics of celestial mechanics guides this intricate dance, demanding an almost perfect understanding of cosmic forces to shepherd a craft towards its distant, glimmering destination. It is a delicate art of cosmic aim, where every fraction of a degree matters in the silent, vast expanse. For the more audacious concepts, such as the Alcubierre warp drive, the theoretical models propose to bend space-time around a vessel, allowing it to travel effectively faster than light without violating local cosmic speed limits. However, the feasibility of such a warp drive necessitates the existence of hypothetical exotic matter. This exotic matter would possess negative mass-energy density, a property that has never been observed in the universe and which pushes the boundaries of known physics. Without this elusive substance, the warp drive remains a captivating but purely theoretical construct. A beautiful mathematical solution without a known physical counterpart. The quiet, profound implications of exotic matter underscore the deep mysteries that still reside at the heart of our understanding of the cosmos, hinting at possibilities that may forever lie beyond our grasp or await a future, revolutionary discovery. It is a silent invitation to unravel the universe's deepest secrets. Given the immense challenges of human survival over such vast distances and timescales, robotic probes stand out as the most feasible first step for interstellar exploration. These uncrewed robotic pioneers are capable of withstanding harsher conditions, including intense radiation and extreme temperatures, and can endure significantly longer travel times than human crews. They do not require complex life support systems, artificial gravity, or protection from psychological challenges. Equipped with advanced instruments, cameras, and artificial intelligence, they can silently gather invaluable data, photograph distant worlds, and send back information about the interstellar medium, paving the way for future human missions. Robotic probes represent humanity's patient, persistent eyes and ears in the distant cosmos, extending our reach without risking human life. They are the quiet, tireless scouts, gracefully venturing into the unknown, laying the groundwork for a future where humanity might follow. Should human crews ever embark on interstellar voyages, the psychological challenges of isolation would be profound. The immense confinement within a spacecraft, the profound distance from Earth, and the sheer duration of interstellar journeys, potentially spanning decades or centuries, would place extraordinary strain on the human mind. The psychological well-being of the crew would be as critical as their physical health. This would necessitate incredibly careful selection processes to identify individuals with exceptional resilience, adaptability, and emotional stability. Furthermore, sophisticated psychological support systems, including virtual reality environments, robust social structures, and engaging activities, would be essential to maintain morale and mental health. It is a subtle, yet crucial aspect of interstellar mission planning, acknowledging the delicate balance between the human spirit and the vast, silent, isolating expanse of deep space. The quiet strength of the human mind would be tested like never before. As for the fuel source for these powerful, future fusion rockets, deuterium offers a promising solution. Deuterium is a heavy isotope of hydrogen, meaning its nucleus contains one proton and one neutron, making it slightly heavier than ordinary hydrogen. It is relatively abundant, found in small but significant quantities in Earth's oceans, and potentially in vast reserves within the atmospheres of gas giants throughout our solar system. This widespread availability means that a future fusion-powered starship could theoretically refuel at various points in its journey, or carry a substantial supply from the outset. The energy released from fusing deuterium atoms is immense and clean, making it an ideal candidate for providing the sustained, powerful thrust needed for interstellar missions. It is a quiet, abundant cosmic resource, patiently awaiting the technological advancements that will allow us to harness its profound energy for the gentle, unhurried journey to other stars. To circumvent the colossal challenge of carrying all necessary fuel for vast distances, a theoretical concept known as the Bussard-Ramjet offers an elegant, if highly ambitious, solution. This visionary propulsion system proposes to scoop up the diffuse hydrogen atoms from the interstellar medium as the spacecraft travels. Imagine a colossal magnetic or electric field acting like a funnel, gently gathering the sparse gas particles in front of the vessel. This collected hydrogen would then be compressed and fed into a nuclear fusion reactor, providing continuous propulsion without the need to carry any fuel from Earth. This ingenious design essentially turns the vast emptiness of space into its own fuel tank, eliminating the exponential mass problem associated with conventional rockets. The Bussard-Ramjet, while deeply theoretical, represents a profound dream of self-sufficiency in the cosmos, a patient, self-sustaining journey through the silent, hydrogen-rich expanse, continuously gathering its energy from the very fabric of space itself. For human crews facing journeys lasting centuries, where even time dilation might not suffice, cryogenic preservation for future revival is a speculative technology often considered. This involves carefully freezing human bodies to extremely low temperatures, halting all biological processes, with the hope of preserving individuals for potential revival in the distant future. The intent would be to awaken them upon arrival at an interstellar destination, allowing them to experience the new world directly. This delicate process faces immense scientific and ethical challenges, including preventing cell damage during freezing and thawing, and the sheer uncertainty of future medical capabilities. Yet, the serene image of voyagers peacefully slumbering through the cosmic night, awaiting a new dawn on a distant planet, remains a powerful vision. It is a quiet, hopeful gamble on future science, allowing the human spirit to bridge millennia of travel, dreaming softly of a new home among the stars, a patient wait for a future that is yet to unfold. Should humanity successfully reach another star system, the ultimate goal for some interstellar missions might be to terraform distant worlds. This ambitious process involves transforming a barren exoplanet, one potentially similar in size and composition to Earth, to make it habitable for human life. This could involve introducing greenhouse gases to warm a frozen world, releasing oxygen into a thin atmosphere, or even engineering ecosystems to create a breathable environment and fertile soil. Terraforming is a monumental, multi-century endeavor, a patient, deliberate act of cosmic gardening on a planetary scale. It represents the profound dream of creating new homes beyond Earth, extending the reach of human civilization and life itself across the galaxy. The vision is one of transforming a desolate landscape into a verdant, thriving world. A slow, elegant act of creation that echoes the universe's own gradual unfolding, nurturing life where none existed before. A testament to humanity's deep connection to life's delicate balance. When selecting these potential new homes, interstellar missions seeking new homes would primarily focus on targeting habitable zones around distant stars. A star's habitable zone, often called the Goldilocks zone, is the region of space around a star where conditions are just right for liquid water to exist on a planet's surface. It's neither too hot, causing water to evaporate, nor too cold, causing it to freeze solid. The presence of liquid water is considered a fundamental requirement for life as we know it, making planets in this serene orbital band prime candidates for potential colonization or the discovery of extraterrestrial life. This careful selection process, guided by our understanding of life's delicate needs, narrows the vast cosmic search to worlds that offer the most promise. It is a patient, focused quest for planets that whisper the possibility of life, beckoning us to explore their temperate shores, a quiet, hopeful search for a new place to call home amidst the countless stars. Beyond the challenges of travel, communication across interstellar distances also requires innovative methods. While conventional radio signals are a starting point, their limitations in range and bandwidth over light-year scales are significant. Therefore, advanced civilizations might employ more sophisticated interstellar communication methods. This could include powerful, tightly focused laser signals, which can transmit data at much higher rates and over greater distances than radio waves, acting like cosmic optical fibers. Alternatively, some speculate about using neutrinos for communication. These ghostly particles barely interact with matter, allowing them to pass through entire planets and stars unimpeded, making them ideal for piercing through dense cosmic regions. However, detecting and generating such signals would require incredibly advanced technology. These methods offer different advantages for long-distance messaging, allowing for a more nuanced and resilient form of cosmic dialogue, a patient, silent exchange of information across the vast, tranquil expanse. For multi-century interstellar journeys, especially those relying on generation ships or deep space habitats, the ability to acquire resources along the way would be invaluable. This leads to the concept of asteroid mining for resources. Future spacecraft might need to mine asteroids, comets, or other small celestial bodies encountered in the vastness of space for essential resources. These could include water, which can be broken down into hydrogen and oxygen for breathable air and rocket fuel, various metals for construction and repair, and other valuable elements. This self-sufficiency reduces the immense launch mass required from Earth and allows for greater mission flexibility and longevity. It is a patient, industrious vision of cosmic exploration, where the journey itself becomes a source of sustenance, transforming the barren rocks of space into vital waypoints. Mining these silent, drifting cosmic resources would be a crucial step in enabling humanity's long, unhurried voyage to the stars. The 1970s saw a remarkable, detailed conceptual study known as Project Daedalus. Designed by the British Interplanetary Society, it was an ambitious blueprint for an uncrewed interstellar probe. This visionary design aimed to reach Barnard's star, located about 6 light-years away, within a time frame of 50 years. The propulsion system proposed was a 2-stage nuclear fusion rocket, utilizing tiny deuterium-tritium pellets ignited by electron beams to create micro-explosions, propelling the craft to a substantial fraction of light speed. Project Daedalus was a testament to the scientific and engineering ingenuity of its time, a meticulous exploration of the practicalities of interstellar flight using then-foreseeable technology. Though never built, it remains a cornerstone of interstellar propulsion research, a patient, detailed roadmap for how humanity might one day send its silent, robotic ambassadors to other stars, a profound whisper of a future yet to unfold. To achieve truly rapid interstellar journeys, minimizing the subjective travel time for human crews, the torch ship concept emerges. A torch ship is a hypothetical spacecraft designed for continuous acceleration throughout the first half of its journey and continuous deceleration throughout the second half. By constantly burning its powerful engines, it would steadily build up speed, potentially reaching a significant fraction of light speed, then gracefully slow down to arrive at its destination. This sustained thrust allows for faster travel times compared to coasting after an initial burn, and crucially, it would also provide a constant sensation of artificial gravity for the crew, pushing them gently against the floor of the vessel. The torch ship represents a powerful, energetic approach to interstellar travel, a continuous, unwavering push through the cosmic ocean, reducing the psychological and physiological stresses of prolonged weightlessness and isolation, offering a more comfortable, yet still incredibly swift, passage. Beyond the more conventional rocket designs, plasma propulsion systems offer an intriguing alternative for long-duration interstellar missions. These systems utilize superheated, electrically charged gas, known as plasma, for thrust. By heating a propellant gas to extreme temperatures and then accelerating the resulting plasma using electromagnetic fields, these engines achieve much higher exhaust velocities and greater fuel efficiency than traditional chemical rockets. While their thrust is typically low, they can operate continuously for very long periods, gradually building up impressive speeds over months and years. This makes them particularly suitable for extended journeys, where sustained, efficient propulsion is paramount. Plasma thrusters are a quiet, elegant solution, a steady, gentle push through the cosmos, gradually accumulating the velocity needed to bridge the vast distances between stars, a patient, efficient method for unhurried, long-duration voyages into the deep, silent reaches of space. Upon arrival at a distant star system, or even during the journey itself, the ability to control a spacecraft's speed with minimal fuel is crucial. This is where magnetic sails for braking and propulsion come into play. These theoretical devices would use powerful, expansive magnetic fields to interact with charged particles flowing from stellar winds or the diffuse interstellar medium. By generating a magnetic field around the spacecraft, it could create a kind of magnetic parachute to slow down by pushing against the incoming charged particles, effectively braking without consuming traditional rocket fuel. Conversely, these sails could also harness the momentum of stellar winds for propulsion, providing a gentle, continuous push. Magnetic sails represent a clever, fuel-efficient way to maneuver in the cosmos, a patient, subtle interaction with the charged particles that permeate space, allowing for graceful deceleration and even acceleration over immense distances, a testament to the elegant forces at play in the universe. Looking far into the distant theoretical future, some scientists ponder the most exotic forms of propulsion imaginable. One such concept is dark energy propulsion, which remains a highly speculative and theoretical idea. Dark energy is the mysterious force believed to be accelerating the universe's expansion, a pervasive, gentle push on the grandest cosmic scales. Harnessing this enigmatic energy for propulsion would involve manipulating the very fabric of space-time itself, a feat that is currently beyond our scientific comprehension. It represents a profound leap in physics, pushing the boundaries of what we understand about the universe's fundamental forces. Should such a breakthrough ever occur, it could offer a pathway to truly revolutionary travel, allowing vessels to traverse cosmic distances with an ease that currently exists only in dreams. This concept whispers of a future where humanity might learn to ride the very expansion of space, a patient, subtle interaction with the universe's grandest, most mysterious force. Another deeply theoretical, almost ethereal concept for propulsion is zero-point energy propulsion. This idea involves tapping into the zero-point energy, which is the minimum energy inherent in the vacuum of space, even at absolute zero temperature. Quantum mechanics suggests that even empty space is filled with a sea of fluctuating virtual particles, possessing a vast, latent energy. If ever understood and controlled, this inexhaustible reservoir of energy could potentially provide limitless propulsion, offering a boundless source of power for interstellar journeys. However, extracting and harnessing this energy remains purely theoretical, a concept that resides at the very edge of our current understanding of physics. It is a quiet, profound whisper of infinite possibility, suggesting that the very emptiness of space might hold the key to its mastery. This speculative notion invites us to ponder the deepest mysteries of the quantum realm and its potential connection to the vastness of cosmic travel, a silent dream of tapping into the universe's own subtle energy. While these exotic concepts remain far-off dreams, more practical advancements are already shaping our approach to interstellar travel. Ion thrusters, for instance, are already in use on some interplanetary missions and represent a step towards more efficient propulsion. These engines work by ionizing a noble gas, typically xenon, and then accelerating the charged ions through an electric field to create a very high-velocity exhaust. The thrust generated by ion thrusters is inherently very low, often no more than the weight of a few sheets of paper. However, they operate continuously for extremely long periods, sometimes for years on end, slowly but steadily building up incredible speeds over months and years of patient, persistent acceleration. This makes them highly fuel efficient and ideal for long-duration missions, where constant, gentle thrust is more important than rapid acceleration. Ion thrusters are a testament to the power of patience in space travel, silently accumulating speed, one ion at a time, for an unhurried journey through the cosmos. As a spacecraft embarks on a journey at speeds approaching that of light, the visual experience of the cosmos would be profoundly altered by relativity and apparent color shifts. Due to the Doppler effect, similar to how the pitch of a siren changes as it passes, the light from be compressed, causing it to appear blue-shifted or bluer than its actual color. Conversely, the light from celestial objects behind the spacecraft would be stretched, causing it to appear red-shifted or redder. Furthermore, the entire sky would seem to warp, with the stars appearing to gather into a brilliant, compressed cone directly in front of the direction of travel, almost empty. This ethereal, beautiful distortion of the cosmic landscape would be a silent, powerful reminder of the incredible speeds being achieved, a testament to the subtle, yet profound interplay between light, motion, and the very fabric of space-time. The journey through the vastness between stars means traversing the interstellar medium, which, while sparse, is far from truly empty. The interstellar medium's composition includes not only extremely dilute gas, primarily hydrogen and helium, and microscopic dust grains, but also pervasive magnetic fields and energetic particles known as cosmic rays. These components, though thinly spread, interact with a passing spacecraft. The magnetic fields can subtly influence the trajectories of charged particles, while cosmic rays pose a radiation hazard. Understanding this subtle cosmic environment is crucial for designing robust spacecraft capable of enduring centuries of exposure. The interstellar medium is a dynamic, albeit quiet, cosmic soup, a gentle tapestry of forces and particles that a starship must patiently navigate, revealing the hidden complexity of seemingly empty space. It is a subtle, yet ever-present part of the cosmic journey, a constant gentle interaction with the ethereal fabric of the galaxy. Given the immense distances between stars, interstellar travel might not always be a single, direct flight. Instead, a more practical approach could involve star hopping for staged journeys. This strategy envisions breaking down the monumental voyage into a series of shorter, more manageable hops using intermediate stars or even unattached rogue planets as waypoints. At each stop, a spacecraft could potentially perform gravity assists to gain velocity, refuel by harvesting resources from asteroids or gas giants, or even deploy smaller probes to scout ahead. This patient, step-by-step approach allows for technological development over time, gradually extending humanity's reach further into the galaxy. It transforms the daunting prospect of a single colossal journey into a series of smaller, achievable steps, a deliberate, unhurried progression across the cosmic landscape, making the vastness slightly less overwhelming. Star hopping is a testament to the power of breaking down large challenges into smaller, more manageable, and patient endeavors. Calculating stable and efficient interstellar trajectories is an incredibly complex undertaking, largely due to what is known as the three-body problem. This mathematical conundrum describes the difficulty of predicting the precise motion of three gravitationally interacting celestial bodies over long periods. In an interstellar context, this complexity is amplified by the gravitational influences of multiple stars, planets, and even dark matter concentrations. The delicate interplay of these forces means that even tiny initial errors in trajectory calculation could lead to immense deviations over light-year distances and centuries of travel. This demands incredibly powerful computational models and constant, precise adjustments to a spacecraft's path. The quiet, intricate dance of cosmic gravity requires a profound understanding of celestial mechanics to guide a vessel safely and efficiently to its distant destination, making precision a paramount virtue in the vast, elegant ballet of the cosmos. As a high-speed interstellar spacecraft traverses the vastness of space, it faces a continuous subtle threat from tiny, fast-moving objects. Protecting such a vessel from collisions with even small asteroids or microscopic micrometeoroids would require incredibly robust and intelligent shielding systems. At relativistic speeds, Even a grain of sand carries immense kinetic energy, capable of puncturing hulls or damaging vital components. Advanced asteroid shields would need to be multi-layered, perhaps incorporating self-healing materials, ablative surfaces that vaporize upon impact, or even electromagnetic fields designed to deflect charged debris. These shields would act as a silent, unwavering guardian, patiently absorbing countless tiny impacts over centuries of travel, ensuring the integrity and safety of the precious cargo within. The development of such resilient protection is as crucial as the propulsion system itself, a quiet, unseen armor against the subtle perils of the cosmic journey. Looking far into the future, the concept of self-replicating probes, often called von Neumann probes, offers a truly revolutionary approach to exploring the galaxy. These hypothetical spacecraft would be designed with advanced artificial intelligence and manufacturing capabilities. Upon reaching a new star system, they would harvest local resources from asteroids, moons, or even gas giants, and use these materials to build exact copies of themselves. These new probes would then launch to other star systems, continuing the process of replication and exploration. This elegant, exponential expansion could theoretically allow a single initial probe to explore vast regions of the galaxy over cosmic timescales, silently spreading its presence across millions of light-years. Von Neumann probes represent a patient, self-sustaining method of exploration, a quiet, inexorable wave of discovery that could eventually map the entire galaxy, a profound testament to the power of autonomous replication in the serene, unhurried cosmos. Within our own solar system, we already employ a clever technique to gain velocity for our probes: gravity slingshots for velocity boosts. This method involves using the gravitational pull of planets, or even stars, to accelerate a spacecraft, much like a slingshot. As a probe swings past a massive celestial body, it steals a small amount of orbital energy from that body, converting it into additional speed for itself. This technique, also known as a gravity assist, is crucial for maximizing the speed of spacecraft with minimal fuel expenditure. It allows missions like the Voyager probes to achieve velocities that would be impossible with their onboard fuel alone, sending them on faster, more efficient trajectories out of our solar system and towards the interstellar medium. The gravity slingshot is a beautiful, elegant dance with cosmic mechanics, a patient, subtle harnessing of the universe's own forces to give our silent explorers an unhurried boost on their long, patient journey. For human crews embarking on the longest interstellar voyages, the design and construction of deep space habitats become an extraordinary undertaking. These habitats must be capable of sustaining human life for centuries in the harsh, isolating environment of deep space, far removed from any planetary support. This demands monumental engineering prowess, ensuring not only advanced life support systems, but also robust structural integrity to withstand radiation, micrometeoroid impacts, and the stresses of prolonged operation. Such a habitat would be a self-contained world, a miniature biosphere drifting silently through the cosmic void, providing a safe, stable, and nurturing environment for generations of travelers. It is a quiet, profound challenge to build a truly enduring home, away from home, a testament to humanity's resilience and ingenuity in the face of the universe's vast, tranquil indifference. The very act of constructing these enduring vessels speaks to a deep, patient commitment to future generations. Integral to the success of these deep space habitats are exceptionally robust life support systems. Interstellar missions, by their very nature, demand systems that can operate without failure for hundreds or even thousands of years, ensuring the continuous survival and well-being of the crew. These systems must be highly redundant, with multiple backups for every critical function and capable of self-repair and adaptation. They would meticulously manage air quality, water recycling, waste processing, and food production, all while maintaining a stable internal environment. The complexity of such long-term, self-sustaining systems is immense, requiring breakthroughs in biology, engineering, and materials science. It is a quiet, continuous act of balancing delicate ecological processes within a confined, artificial world, a testament to the meticulous planning required for humanity's most ambitious journeys. The silent, tireless operation of these systems would be the heartbeat of any interstellar vessel, ensuring life's gentle persistence. Even with the most advanced technology imaginable, interstellar communication faces a fundamental, unyielding barrier: the speed of light. This means that transmitting large amounts of data back to Earth from interstellar distances would be extremely slow. A probe at 4 light-years would take 4 years for its signals to reach us, regardless of how powerful its transmitter or how sensitive our receivers. This limited data transmission rate means that information would trickle back over immense timescales, rather than gush in real-time streams. Scientists would need to be patient, waiting years for images, scientific readings, or even simple status updates. This quiet, persistent delay profoundly shapes how we gather knowledge from the distant cosmos, emphasizing the value of carefully curated data and highly autonomous onboard analysis. It's a reminder that even in an era of rapid information, the universe imposes its own serene, unhurried pace on our cosmic conversations. As we contemplate the possibility of our own interstellar voyages, the great silence as a cosmic puzzle often resonates deeply. This refers to the perplexing absence of observed evidence of extraterrestrial life, despite the high probability that intelligent civilizations should exist somewhere in our vast universe. If interstellar travel is possible, and many stars host potentially habitable planets, why have we not detected any signs of other life? No signals, no probes, no grand structures. This profound aspect of the Fermi paradox deeply influences interstellar travel discourse, prompting scientists to consider whether there are unseen filters that prevent civilizations from emerging or from achieving interstellar capabilities. It is a quiet, persistent question that echoes through the vastness of space, urging humility and a careful re-evaluation of our assumptions about life's prevalence and its journey across the cosmos. The silence itself becomes a powerful, contemplative enigma. As an alternative to sending adult humans, facing the immense challenges of a multi-century journey, some concepts propose the cryogenic preservation of human embryos or genetic material. This approach would involve sending tiny, cryogenically frozen embryos, or simply the genetic blueprints of humanity, aboard a robotic probe. Upon arrival at a suitable exoplanet, advanced artificial intelligence would then be tasked with growing and raising these new generations of humans in a carefully designed environment. This method bypasses many of the physiological and psychological challenges of adult human travel, offering a more compact and resilient way to seed new worlds with human life. It is a quiet, profound act of future-proofing humanity, a patient gamble on the capabilities of artificial intelligence and the resilience of our genetic heritage, gently entrusting the future of our species to silent, robotic guardians on a long, unhurried journey across the stars. Regardless of whether human crews or embryos are on board, highly advanced artificial intelligence for autonomy would be indispensable for interstellar missions. Given the light-speed delays in communication, an interstellar probe or starship must be capable of operating with extreme independence. AI would be responsible for autonomous navigation, making real-time course corrections, identifying and avoiding hazards, and managing the complex array of spacecraft systems. It would also handle system maintenance, performing repairs and diagnostics, and making critical scientific decisions, such as selecting optimal targets for observation or designing experiments on the fly. This level of self-sufficiency is vital for missions that operate far beyond the reach of immediate human control. The quiet, tireless intelligence of these machines would be the unseen pilot and engineer, patiently guiding the vessel through the vast, silent cosmos, ensuring the mission's graceful continuity over millennia. While practical interstellar travel focuses on achieving a fraction of light speed, science fiction often explores the tantalizing idea of instantaneous travel. Quantum tunneling for instant travel is a highly speculative concept, sometimes invoked in these narratives. Quantum tunneling is a real phenomenon in quantum mechanics, where a particle can pass through an energy barrier even if it does not have enough energy to classically overcome it. However, this phenomenon applies to subatomic particles over extremely short distances and is fundamentally not supported by current physics for macroscopic objects like spacecraft. The idea of a starship instantly appearing at a distant destination through a quantum shortcut remains firmly in the realm of theoretical fantasy, a beautiful, quiet dream that stretches the boundaries of our understanding. It is a silent reminder of the vast gulf between quantum curiosities and the grand scale of cosmic journeys, a wish for a universe where distances are effortlessly erased. To power truly advanced interstellar propulsion systems, or even sustain massive deep space habitats, an enormous and continuous supply of energy would be required. This leads to the hypothetical concept of Dyson spheres for energy harvesting. A Dyson sphere is a megastructure that could, in theory, encapsulate an entire star, capturing nearly all of its energy output. By surrounding a star with a vast array of solar collectors or habitats, a civilization could tap into an energy source far exceeding anything available on a planetary surface. Such immense, harnessed stellar energy could then potentially power advanced interstellar propulsion systems, drive massive terraforming projects, or sustain entire civilizations traveling through space. It is a quiet, colossal vision of future engineering, transforming a star into a perfectly controlled energy source, a patient, subtle re-engineering of the cosmic landscape to fuel humanity's grandest ambitions, a testament to the boundless potential of advanced civilizations. The concept of interstellar arcs for preservation addresses the profound challenge of carrying life and culture across the vast cosmic void. These would be enormous, self-contained vessels, far larger than any spacecraft imagined today, designed to carry entire populations of humans, complete biospheres, or vast genetic libraries to new star systems. The goal would be to preserve life and culture, ensuring the continuity of a species or an ecosystem, even if Earth were to face an existential threat. These arcs would be slow, patient journeys, perhaps taking thousands of years, but their purpose is profound: to safeguard the delicate tapestry of life. They represent a quiet, enduring hope for the future, a testament to our innate drive to preserve and propagate, carrying the gentle spark of existence to new, distant shores. These colossal vessels would be silent, floating sanctuaries, cradling the essence of life on its long, unhurried passage through the cosmos. Building upon the legacy of Project Daedalus, a modern international study known as Project Icarus aims to re-evaluate and update that ambitious concept. Project Icarus is a collaborative effort by scientists and engineers to design a feasible uncrewed interstellar probe, leveraging contemporary understanding and technology. The goal remains to create a detailed blueprint for a spacecraft capable of reaching a nearby star system, like Alpha Centauri, within a reasonable timeframe. This modern study critically examines propulsion methods, shielding requirements, navigation, and power systems, integrating advances in materials, science, computing, and miniaturization. It is a quiet, patient, and rigorous intellectual endeavor, building upon past dreams to forge a more realistic path toward interstellar exploration. Project Icarus represents humanity's persistent, evolving commitment to the dream of reaching the stars, a testament to our capacity for sustained collective scientific pursuit, and the patient refinement of our cosmic aspirations. The relativistic rocket equation, a profound extension of Tsiolkovsky's classical rocket equation, starkly demonstrates a fundamental limitation for interstellar travel. It reveals with elegant precision that to accelerate even a small mass, such as a spacecraft, to a significant fraction of light speed, the required fuel mass increases exponentially. This means that for conventional chemical rockets, or even more advanced nuclear fission rockets, the mass of fuel needed quickly becomes impossibly large, far exceeding the total mass that could realistically be launched from Earth. This profound physical reality underscores why entirely new propulsion paradigms, beyond simply burning more fuel, are absolutely essential for bridging the immense cosmic distances. It demands innovative approaches to energy and thrust that gently defy our current understanding of conventional physics, prompting a quiet re-evaluation of our methods. The elegance of the equation quietly highlights the scale of the challenge, a silent mathematical barrier to conventional acceleration, compelling us to dream of more subtle and efficient ways to move through the cosmos. This fundamental constraint ensures that the journey to other stars will always be an endeavor of profound ingenuity, pushing the very limits of our scientific and engineering capabilities, a patient quest for novel solutions. Before a vessel truly enters the vast, open expanse between stars, it must first gracefully exit the protective bubble of our sun's influence. Our solar system continuously pushes against the interstellar medium, creating a subtle phenomenon known as a bow shock, much like a gentle wave created by a boat moving through water. Beyond this dynamic interaction lies a crucial and distant boundary, the heliopause, which marks the outermost edge of the sun's magnetic field and the reach of its solar wind. Our pioneering Voyager 1 and 2 spacecraft, after decades of patient travel, have now serenely crossed this distant threshold, marking humanity's first gentle entry into the true interstellar space. This quiet passage signifies a monumental achievement, a subtle step beyond our familiar cosmic home and into the wider, more tranquil ocean of the galaxy. It is a patient unfolding of our reach into the unknown, a testament to the enduring spirit of exploration that quietly propels us outward. The Voyager's journey beyond this boundary offers us direct, whispered insights into the nature of the space between stars, a serene frontier. Once beyond the heliopause, a spacecraft would begin its long, unhurried traverse through the interstellar medium itself. While often imagined as a perfect, empty void, this vast expanse is a dynamic, albeit incredibly diffuse, environment. It contains not only wisps of dilute gas, predominantly hydrogen and helium atoms. This ethereal cosmic soup is a silent, complex tapestry of forces and particles, subtly interacting with any passing vessel over immense distances. Understanding its delicate composition and tranquil behavior, as these seemingly benign elements can pose unique challenges, particularly at high velocities. The interstellar medium, in its serene vastness, is a constant, gentle reminder of the subtle complexities hidden within what appears to be emptiness, revealing a universe that is always more intricate than it first appears, even in its quietest corners. A key objective of future interstellar probes, especially those designed for long-duration missions, would be a gentle quest for cosmic companionship, searching for biosignatures on exoplanets. This involves detecting chemical indicators of life in the atmospheres or on the surfaces of distant exoplanets. Scientists would analyze the light passing through an exoplanet's atmosphere, looking for specific combinations of gases, such as oxygen, methane, or ozone, that are often produced by biological processes. The presence of these biosignatures, or even more complex molecules, could provide indirect evidence of life beyond Earth. It is a patient, meticulous search for the subtle whispers of biology across the vast cosmic ocean, a hopeful endeavor to understand if life, in its myriad forms, is a common or rare phenomenon in the universe. This silent scientific quest shapes the design of our most advanced instruments, aiming to gently uncover the secrets of distant worlds and their potential for life, deepening our connection to the wider cosmos. Reaching high speeds is, surprisingly, only half the battle in the grand scheme of interstellar travel. The challenge of deceleration, effectively slowing a spacecraft upon arrival at a target star system, without using an equivalent, immense amount of fuel, is another immense engineering hurdle. If a vessel accelerates to a significant fraction of light speed, it carries an enormous amount of kinetic energy. To stop or even orbit a distant star system, this energy must be gracefully dissipated. This might involve innovative techniques such as magnetic sails interacting with stellar winds, or even reverse ramjets that scoop up interstellar gas to create drag. The elegant art of slowing down, of bringing a swift vessel to a gentle halt in the cosmic ocean, is as critical and complex as the initial acceleration. It speaks to a balanced approach to cosmic journeys, where the beginning and end of the voyage demand equal ingenuity, ensuring a serene, controlled arrival at a distant, silent destination. Sometimes, the universe brings its wonders to us, offering a glimpse into other star systems without humanity needing to travel there. This occurs through interstellar objects passing through our solar system. In recent years, astronomers have detected objects like Oumuamua and Borisov, which originated from beyond our sun's gravitational influence and were merely passing through our cosmic neighborhood before continuing their silent journey back into the interstellar void. These rare cosmic visitors confirm that interstellar objects exist, providing invaluable scientific data about the composition and processes occurring in other star systems. They are like cosmic gifts, silent messengers from distant stellar nurseries, offering a tangible connection to the wider galaxy without the need for an arduous interstellar voyage. Their transient, unhurried passage through our system offers a unique, tranquil opportunity to study the material from alien suns, enriching our understanding of the cosmos in a surprisingly passive yet profound way. The Great Filter hypothesis is a theoretical barrier that seeks to address the profound silence of the cosmos, potentially explaining the Fermi paradox. This hypothesis suggests that at some point in the long evolutionary path from the emergence of life to the achievement of advanced interstellar travel, there exists a filter, a highly improbable or catastrophic step that prevents civilizations from reaching an advanced, galaxy-spanning stage. This filter could be in our past, such as the initial emergence of life or complex multicellularity, or it could lie in our future, perhaps an inevitable self-destruction or a fundamental limit to technological growth. The Great Filter is a theoretical barrier that prevents civilizations from reaching advanced interstellar travel, either in their past or in their future, potentially explaining the Fermi paradox. It is a quiet, contemplative challenge to our assumptions about cosmic evolution, prompting us to ponder the delicate balance of existence and the subtle hurdles that may prevent life from spreading widely across the stars, making the universe's silence all the more profound. A more cautious and perhaps unsettling explanation for the cosmic silence is the dark forest theory of interstellar relations. This theory suggests that advanced alien civilizations might remain deliberately silent, fearing that any broadcast or detectable activity would reveal their location and invite destruction from other, more aggressive species. In this chilling cosmic scenario, the universe is seen as a dark forest, where every civilization is a hunter, and revealing one's presence is an act of profound danger. Therefore, the wisest course of action for any advanced civilization is to remain perfectly quiet, hidden, and undetectable. This theory frames the apparent absence of alien signals not as a lack of life, but as a strategic, silent act of self-preservation. It is a somber, almost melancholic perspective on interstellar interaction, suggesting a universe where caution reigns supreme and silence is a necessary, gentle form of defense, a quiet cosmic strategy born of profound experience. Given the light speed delay in communication across interstellar distances, spacecraft autonomy for unforeseen events becomes an absolute necessity for any mission. Interstellar probes and starships would need to possess extremely high levels of autonomy to respond effectively to unexpected problems, system failures, or sudden scientific opportunities without immediate human intervention. A probe at Proxima Centauri, for example, cannot wait 8 years for instructions from Earth if a critical system fails or if it encounters an unexpected phenomenon. Its onboard artificial intelligence must be capable of independent decision-making, problem-solving, and even adapting its mission parameters. This quiet self-reliance ensures the mission's continuity and effectiveness over vast distances and timescales, transforming the spacecraft into a truly independent explorer. It is a testament to the sophistication of future AI, patiently navigating the unknown with quiet confidence, a silent partner in humanity's quest for cosmic knowledge. Revisiting a powerful yet controversial concept from the mid-20th century, the Orion drive involved using nuclear pulses for propulsion. This ambitious method proposed propelling a massive spacecraft by detonating a series of nuclear explosions behind it. Each controlled detonation would create a powerful plasma pulse that would impact a large, robust end, imparting a significant thrust. While theoretically capable of achieving very high speeds and propelling enormous payloads, the Orion drive raised substantial environmental and ethical in space. Despite its immense power, this method was ultimately deemed impractical and too hazardous to pursue. The Orion drive remains a powerful, yet ultimately unpursued vision in the history of interstellar travel concepts, a silent, almost dramatic testament to humanity's early, bold imaginings of how to bridge the cosmic distances. It reflects a time when grand, powerful solutions were sought, even if they carried significant, quiet risks. Looking beyond our current operational spacecraft, NASA has actively studied concepts for an interstellar probe mission. This ambitious proposal envisions a spacecraft designed to travel an astonishing 1,000 astronomical units from the Sun within a time frame of just 50 years. An astronomical unit, or AU, represents the average distance between Earth and the Sun, so 1,000 AU is an immense distance, far beyond the heliopause and deep into the interstellar medium. Such a mission would push the boundaries of our solar system, offering unprecedented insights into the conditions and composition of the space between stars. It represents a patient, long-term commitment to cosmic exploration, a quiet, deliberate expansion of our sensory reach into the vast, tranquil ocean beyond our stellar home. This planned probe would be a silent scout, charting unknown territories and extending humanity's presence into the deeper cosmos. For these groundbreaking missions, whether crewed or uncrewed, the role of artificial intelligence for exploration would be paramount. Highly advanced AI could analyze the vast amounts of data streaming back from interstellar probes, identifying anomalies, recognizing patterns, and even designing new experiments on the fly. This capability would greatly enhance scientific returns, allowing the probe to adapt its observations and investigations based on unexpected discoveries, far beyond what could be pre-programmed from Earth. Given the immense communication delays, such intelligent autonomy is not just beneficial, but absolutely essential. The AI would become a tireless, patient scientist aboard the vessel, making real-time decisions and ensuring that every precious moment of the long journey is utilized to its fullest scientific potential. It is a quiet partnership between human curiosity and machine intelligence, gently guiding the quest for knowledge across the vast, silent reaches of space. For journeys stretching across centuries, the longevity of the spacecraft itself becomes a critical concern. Interstellar probes designed for such immense durations would require incredibly sophisticated self-repairing systems for longevity. These systems would be capable of detecting malfunctions, diagnosing problems, and even fabricating replacement parts using onboard resources. Imagine a spacecraft that can quietly mend itself, repairing minor damage from micrometeoroid impacts or replacing worn components without human intervention. This self-maintaining capability would be crucial for ensuring operational continuity over hundreds or even thousands of years in the unforgiving environment of deep space. Such resilience would allow a probe to patiently endure the rigors of cosmic travel, extending its lifespan far beyond conventional designs, ensuring that its mission of discovery continues gracefully through the epochs. It is a quiet testament to enduring engineering, allowing our robotic explorers to persist in the vast, tranquil void. Given the inherent difficulties and technological demands of achieving near-light speeds, another approach to interstellar travel perhaps more patient and achievable in the nearer term, is the slow boat approach. This concept involves sending slower, but incredibly robust and self-sustaining probes, or generation ships. Rather than striving for rapid transit, this strategy accepts much longer travel times, perhaps thousands or tens of thousands of years, in exchange for relying on simpler, more reliable technology. These vessels would be designed for extreme longevity and self-sufficiency, becoming self-contained worlds drifting peacefully through the cosmos. The slow boat emphasizes endurance and resilience over speed, allowing for a more gradual, unhurried journey where the voyage itself becomes a way of life or a long-term scientific endeavor. It is a quiet, philosophical alternative, a patient acceptance of the universe's grand timescales, valuing the journey as much as the destination. For future interstellar missions, particularly those aiming to establish outposts or refuel, finding water ice for propellant would be a crucial strategic advantage. Locating sources of water ice on comets, asteroids, or moons within target star systems could provide essential propellant for both the main spacecraft and any smaller probes it carries. Water can be electrolyzed to produce hydrogen and oxygen, which are powerful rocket propellants. This ability to harvest fuel from local resources significantly reduces the need to carry all propellant from Earth, vastly decreasing launch mass and increasing mission flexibility. It transforms distant celestial bodies into cosmic gas stations, enabling longer, more ambitious explorations. This patient, resourceful approach to interstellar travel would allow humanity to extend its reach more efficiently, turning the quiet, icy bodies of other star systems into vital stepping stones for deeper cosmic journeys. The Breakthrough Starshot initiative epitomizes a radical new vision for interstellar travel with its concept of tiny probes. This ambitious project proposes sending gram-scale nanocraft into space. These miniature vessels, each equipped with cameras, sensors, and communication systems. The goal is to accelerate these tiny probes, allowing them to reach the Alpha Centauri system within mere decades. The immense challenge lies in miniaturizing all necessary components to an extreme degree while ensuring their resilience in the harsh space environment. This innovative approach offers a path to genuine interstellar exploration within a human lifetime. Our smallest creations can travel the fastest, becoming our silent, swift ambassadors to other stars. It is a profound testament to the power of miniaturization and focused energy. However, even with the most advanced shielding, the problem of cosmic debris remains a persistent, subtle threat. Even small specks of dust or microscopic micrometeoroids, though tiny, become incredibly dangerous projectiles when a spacecraft is traveling at relativistic speeds. These particles, abundant in both our own solar system and potentially in other star systems, could be devastating to a spacecraft, causing catastrophic damage upon impact. The kinetic energy of such collisions would be immense, capable of puncturing hulls or disabling vital systems. This demands incredibly robust and intelligent shielding systems, perhaps combining ablative materials with active electromagnetic fields to protect the delicate instruments and any potential crew. It is a quiet, continuous threat, a constant, gentle reminder that even the vast emptiness of space holds its own pervasive perils, requiring vigilant protection for any vessel daring to traverse its immense, tranquil distances. To counter the omnipresent threat of charged particles and cosmic dust at high velocities, magnetic deflector shields offer an elegant solution. For high-speed interstellar travel, these shields would create a protective bubble around a spacecraft by generating powerful magnetic fields. These fields would gently push aside charged particles, such as those found in stellar winds or cosmic rays, and potentially even some larger dust grains, preventing them from striking the vessel directly. This active shielding mechanism reduces the need for heavy, passive armor, allowing for lighter and faster spacecraft designs. It is a quiet, invisible embrace of protection, using the subtle forces of electromagnetism to create a safe passage through the turbulent, charged environment of space. Magnetic deflector shields represent a sophisticated, patient approach to safeguarding interstellar travelers, transforming the hostile cosmic environment into a more serene path for exploration, a delicate dance with unseen forces. A truly remarkable and passive tool for interstellar exploration is gravitational lensing as a natural telescope. Our Sun's immense gravity, when viewed from a great distance, can act as a giant lens, bending and magnifying light from distant objects. A probe sent far enough to a precise location thousands of astronomical units from the Sun could use this natural phenomenon to study exoplanets with unprecedented detail. The Sun's gravity would focus the faint light from distant worlds, essentially creating a colossal telescope, allowing astronomers to potentially resolve surface features or analyze atmospheric compositions with extraordinary clarity. This is a patient, long-term scientific endeavor, requiring decades of travel to reach the focal point of this natural lens. It is a quiet, profound harnessing of cosmic forces, allowing us to peer across immense distances with a clarity that would otherwise be impossible, a testament to the subtle, elegant power of gravity in shaping our understanding of the universe. Finally, sustaining power for centuries-long missions presents a unique and persistent challenge. The challenge of powering interstellar probes is immense because solar power, so effective near our Sun, diminishes rapidly with distance. Far beyond the heliopause, sunlight is too faint to be a primary energy source. Therefore, these probes require innovative solutions like radioisotope thermoelectric generators, which convert the heat from the slow, gentle decay of radioactive materials into electricity, providing a steady, reliable power source for decades. For even longer missions, or those requiring more power, small fission reactors might be necessary. These compact nuclear power sources could provide a robust and long-lasting energy supply, independent of stellar proximity. It is a quiet, continuous act of harnessing enduring forms of energy to fuel humanity's patient, unhurried journey through the vast, dark expanse of the cosmos, ensuring that the lights of discovery never fade. Beyond the quiet search for biosignatures, a key objective for future interstellar probes would be an even more ambitious quest: the search for technosignatures. These are evidences of technology from alien civilizations, subtle whispers of intelligence across the cosmos. Such technosignatures could include artificial structures, like immense megastructures orbiting stars, or deliberate communication signals, perhaps in radio waves or laser pulses, that stand out from natural cosmic phenomena. Detecting these would provide profound evidence of intelligent life elsewhere in the universe, transforming our understanding of our place in the cosmos. It is a patient, careful listening for echoes of other minds, a silent, hopeful outreach across the vast, tranquil expanse. This search for the deliberate imprints of other civilizations on the cosmic canvas guides the design of our most sensitive instruments, hoping to gently uncover the presence of distant, technological peers. For any interstellar spacecraft, especially those designed for decades or centuries of operation, the importance of redundancy cannot be overstated. Given the impossibility of sending repair missions over such vast distances and timescales, every critical component within the vessel would need multiple backup systems. Imagine a ship where every essential function, from life support to propulsion, from navigation to power generation, has several independent safeguards ready to activate should a primary system fail. This layered approach to reliability ensures that the mission can gracefully endure unexpected failures, patiently continuing its journey even in the face of adversity. It is a quiet, meticulous dedication to resilience, building in multiple pathways for survival and operation, ensuring the continuous, unhurried progress of the spacecraft through the silent, indifferent cosmos. Redundancy is the silent guardian of longevity, a testament to careful, anticipatory design. The selection of potential interstellar destinations is a profound decision, deeply informed by the field of astrobiology. Astrobiology's role in destination selection is crucial. guiding our focus to identify star systems and exoplanets most likely to host life, or at least conditions suitable for it. This involves studying the types of stars that offer long-term stability, analyzing exoplanet atmospheres for signs of water or other essential chemicals, and considering factors like planetary size, temperature, and geological activity. By applying our understanding of life's delicate requirements, astrobiologists help narrow the immense cosmic search to the most promising candidates, ensuring that our patient journeys are directed towards worlds that whisper the possibility of biological wonders. It is a quiet scientific quest to find echoes of Earth's vibrant life across the galaxy, a gentle, informed choice that shapes the very purpose of our interstellar endeavors. Guiding our silent probes towards the most alluring cosmic havens. One of the most elegant and fuel-efficient principles for interstellar propulsion is the light sail principle. This concept involves harnessing the momentum of photons, tiny packets of light, for propulsion. Much like a sailboat catches the wind, a vast, ultra-thin, and highly reflective light sail catches the gentle but continuous pressure exerted by photons streaming from a star or a powerful laser. While the force from individual photons is minuscule, over time, this gentle push can accelerate a spacecraft to incredibly high speeds without needing any onboard fuel. This absence of propellant makes light sails exceptionally efficient for long-duration missions. It is a quiet, graceful dance with the fundamental particles of light, slowly but persistently building up momentum, allowing a spacecraft to drift with serene purpose across the vast, silent ocean of space, a testament to the subtle power of light itself. Our understanding of the boundary between our solar system and the wider galaxy was profoundly enhanced by the Interstellar Boundary Explorer, or IBEX. This remarkable NASA mission mapped the boundary between our solar system and interstellar space, providing crucial data about the heliopause and the flow of interstellar particles. IBEX did not physically cross this boundary, but rather detected particles that had interacted with it, creating a map of this distant, dynamic frontier. Its observations revealed the complex interactions occurring where the sun's influence gently gives way to the interstellar medium, showing us how our solar system truly moves through the galaxy. IBEX was a silent, distant observer, patiently gathering data that unveiled the subtle, yet grand cosmic forces shaping our stellar neighborhood, offering a quiet, unprecedented glimpse into the very edge of our cosmic home and the gentle embrace of the interstellar void. A compelling, yet speculative idea regarding advanced alien civilizations is the cosmic zoo hypothesis. This theory suggests that advanced extraterrestrial civilizations might choose not to interfere with less developed ones, such as humanity, observing them from a distance, much like we might observe animals in a cosmic zoo. According to this idea, our apparent isolation is not due to a lack of other life, but rather a deliberate policy of non-interference by more advanced beings. They might allow civilizations to develop naturally, without intervention, patiently watching our evolution unfold. This hypothesis offers a tranquil explanation for the Great Silence, suggesting that the universe is not empty, but rather filled with silent observers. It is a quiet, humbling thought that humanity might be part of a vast, unseen cosmic experiment, gently guided by unseen hands, a profound and patient watchfulness from afar. For long-duration human missions, where the crew would experience weightlessness for decades or centuries, the role of artificial gravity through rotation becomes a practical necessity for health and well-being. Spinning a spacecraft to create centrifugal force can effectively simulate gravity, gently pushing the crew and objects towards the outer hull of the rotating section. This continuous, artificial gravitational pull would mitigate the severe negative health effects of prolonged weightlessness, such as muscle atrophy, bone density loss, and cardiovascular issues. It would also provide a more familiar and psychologically comfortable environment for the crew, a quiet anchor in the profound disorientation of deep space. This elegant solution allows for a more humane and sustainable approach to long-term human spaceflight. ensuring the gentle health and stability of voyagers on their unhurried journey to other stars, a serene and practical adaptation to cosmic travel. Instead of attempting a single monumental leap across light years, some theories suggest that civilizations might adopt a more gradual approach, the planet-hopping strategy. This involves colonizing nearby planets within their own star system first, establishing a strong base and then slowly expanding outward to the next closest star system. This gradual, patient expansion would proceed step by step, gradually extending a civilization's reach across the galaxy over vast timescales. This approach reduces the immediate technological demands of a single colossal interstellar journey, allowing for incremental advancements and resource utilization at each new system. It is a quiet, methodical way of spreading across the cosmos, a slow, deliberate colonization that echoes the natural processes of life's expansion. Planet hopping offers a less dramatic, but perhaps more pragmatic pathway for a civilization to patiently fill the vast, tranquil expanse of the galaxy with its presence. For human crews embarking on multi-decade or multi-century journeys, the challenge of maintaining crew morale would be paramount. The immense isolation, confinement, and the sheer duration of the voyage, coupled with the knowledge that Earth is light years away and possibly centuries in the past, would place profound psychological strain on individuals. Maintaining psychological well-being and morale would require careful planning for social structures, engaging activities, mental health support, and even a sense of evolving purpose. Crew members would need to be exceptionally resilient, adaptable, and emotionally stable, supported by a carefully designed environment that fosters community and psychological health. It is a quiet, continuous act of nurturing the human spirit in the face of cosmic immensity, ensuring that the inner world of the crew remains as stable as the outer world of the ship. The delicate balance of human psychology is as crucial as any engine on such a long, unhurried passage. Finally, for uncrewed interstellar robotic probes, the need for robust autonomy in robotics is absolute. Given the light speed delays that make real-time human control impossible, these probes must be capable of operating with exceptionally high degrees of independence. They would need to make complex decisions, conduct intricate experiments, and even troubleshoot unexpected problems without any real-time human input. This level of autonomy requires incredibly sophisticated artificial intelligence, capable of learning, adapting, and innovating in response to unforeseen circumstances. The probe effectively becomes its own explorer and scientist, patiently navigating the unknown, making its own discoveries, and gracefully handling any challenges that arise. It is a quiet, tireless dedication to self-reliance, ensuring that humanity's distant eyes and ears in the cosmos can continue their mission of discovery, unhindered by the vast distances and the gentle, unhurried pace of light. While humanity dreams of sending its own probes to distant stars, we also patiently listen for signals from others. The Breakthrough Listen initiative is a profound project dedicated to searching for intelligent extraterrestrial communications across the cosmos. Using powerful radio telescopes, this ambitious program scans millions of star systems for any evidence of artificial signals, including potential transmissions from interstellar probes or even entire alien civilizations. It is a quiet, persistent act of cosmic listening, hoping to detect a whisper of intelligence amidst the vast, natural symphony of the universe. The project aims to cast a wide net, patiently sifting through immense amounts of data for any pattern that suggests a non-natural origin. Breakthrough Listen embodies humanity's deep yearning for connection, a silent, hopeful search for companionship across the immense, tranquil expanse of galaxies, patiently waiting for an echo from afar. For the most ambitious human interstellar missions, particularly those involving multi-generational journeys, the world ship concept emerges as a profound solution. A world ship is an extremely large interstellar vessel designed to be a completely self-sustaining habitat, effectively carrying an entire society or ecosystem. Imagine a colossal, self-contained world, complete with its own agriculture, infrastructure, and social structures, drifting peacefully through the cosmos. These ships would be designed for immense longevity, allowing multiple generations to live, reproduce, and pass away aboard the vessel before the destination star system is reached. The world ship is not just a mode of transport, it is a moving civilization, a quiet, enduring ark, preserving human life and culture across the vast, silent sea of stars. It represents a patient, deeply committed vision for humanity's future beyond Earth, a testament to our capacity for sustained existence and the gentle unfolding of life across cosmic timescales. If cryosleep were to become a viable technology for human interstellar travel, it would introduce a profound ethical and practical challenge known as the sleeping beauty problem. This problem addresses the complexities of reviving people centuries later into a vastly different society. Imagine waking up to a world utterly transformed, where language, culture, technology, and even the fundamental values of humanity have shifted beyond recognition. The sleeping beauty problem encompasses the psychological impact on the revived individuals, the legal and social implications of their reintegration, and the moral responsibility of those who send them. It is a quiet, contemplative question about the nature of time, identity, and societal evolution. While cryosleep offers a pathway to bridge cosmic distances for individuals, it also highlights the delicate balance between personal experience and the relentless, unhurried march of cosmic history, demanding careful consideration of a future that may feel entirely alien. Reflecting a long-term vision for humanity's future in space, the United States Congress passed the Interstellar Travel Act of 2005. This legislation, while largely symbolic, served to encourage private sector investment and research into the ambitious goal of interstellar travel. By recognizing the profound importance of venturing beyond our solar system, the Act subtly signaled a national aspiration and a commitment to pushing the boundaries of human exploration. It represents a quiet, forward-looking gesture, a patient acknowledgement that the journey to the stars will require not only scientific ingenuity, but also sustained societal support and economic investment. The Interstellar Travel Act, in its legislative elegance, reflects a deep-seated human desire to explore, gently guiding future endeavors and fostering the quiet, persistent pursuit of cosmic dreams, a testament to the enduring allure of the unknown. For certain advanced propulsion concepts, such as laser sails, the importance of miniaturization is absolutely critical. To achieve the incredibly high acceleration rates required to reach a significant fraction of light speed, the mass of the spacecraft must be reduced to an absolute minimum. This means that every component, from cameras and sensors to power sources and communication systems, must be designed to be incredibly tiny, often weighing only grams. Extreme miniaturization of spacecraft components is essential to achieve high acceleration rates with minimal mass, allowing the gentle but continuous push of a laser beam to propel them to astonishing velocities. It is a quiet revolution in engineering, pushing the boundaries of what is possible on a microscopic scale to achieve macroscopic cosmic journeys. This delicate art of compact design is crucial for making swift, unhurried travel to other stars a tangible reality, a testament to the power of small, elegant solutions in the vastness. Should multiple intelligent civilizations exist across the galaxy and engage in interstellar travel, it is plausible to imagine the formation of an interstellar communication network. This network would be a vast, intricate web of communication pathways, allowing different species to share knowledge, experiences, and cultural insights across cosmic distances. Imagine a quiet, ongoing dialogue spanning light years, where information flows patiently between star systems, enriching the understanding of all participating civilizations. Such a network would require common protocols, advanced encryption, and perhaps even dedicated relay stations to bridge the immense spatial and temporal gaps. It is a profound, hopeful vision of cosmic unity, a silent intellectual collaboration that transcends the boundaries of individual star systems. The existence of such a network would transform the Great Silence into a symphony of shared wisdom, a gentle, patient exchange of ideas across the tranquil, star-strewn canvas of the galaxy. A particularly intriguing variant of the cosmic zoo idea is the zoo hypothesis. This theory suggests that extraterrestrial intelligences, perhaps far more advanced than humanity, deliberately avoid contact with Earth to allow our civilization to develop naturally, without external interference. They might observe us from a distance, patiently waiting for humanity to reach a certain level of technological or social maturity before making their presence known. This non-interference policy, often referred to as the prime directive in science fiction, would explain the apparent lack of alien contact despite the high probability of their existence. It is a quiet, almost benevolent explanation for the cosmic silence, implying a gentle, patient stewardship from afar. The zoo hypothesis offers a profound, humbling perspective, suggesting that humanity's journey of discovery and evolution is being silently watched, a delicate, unhurried unfolding under the gaze of unseen cosmic guardians. While concepts like laser sails and antimatter drives promise rapid transit, the practicality of slow probes remains a cornerstone of current interstellar exploration. Less glamorous perhaps, but incredibly reliable, slow conventional probes, like the Voyages, are currently our only proven method for reaching interstellar space. These hardy vessels, launched decades ago, patiently drift through the cosmos at speeds far below a fraction of light speed, gradually accumulating distance over very long timescales. They demonstrate that even with existing technology, we can send our emissaries beyond the heliopause, patiently gathering invaluable data about the interstellar medium. This slow and steady approach emphasizes endurance, resilience, and long-term commitment over speed. It is a quiet, persistent testament to the power of gradual progress, ensuring that humanity's reach, however unhurried, continues to expand into the vast, tranquil unknown. A fundamental barrier to achieving rapid interstellar travel is the immense energy cost of relativistic travel. The energy required to accelerate a spacecraft to a significant fraction of the speed of light scales exponentially with the square of its velocity. This means that even tiny increases in speed, especially as one approaches the light barrier, demand enormous and rapidly escalating amounts of energy. For example, doubling a spacecraft's speed from a tenth to a fifth of light speed would require far more than double the energy. This profound physical reality is why achieving even a small fraction of light speed is such a monumental challenge. It is a quiet, uncompromising law of physics dictating that the faster we wish to travel, the more colossal the energy expenditure becomes. This fundamental constraint ensures that the quest for swift interstellar journeys will always push the very limits of our energy generation capabilities, a patient, profound challenge to our ingenuity. Finally, at the very edge of theoretical speculation, some concepts explore the possibility of harnessing the universe's most enigmatic components for propulsion. The dark matter as potential fuel is one such highly speculative idea. Dark matter, the mysterious substance that makes up about 85% of the universe's total mass, interacts only through gravity and is currently undetectable directly. Similarly, dark energy, which drives the universe's accelerating expansion, remains an enigma. Some theoretical concepts explore the possibility of harnessing dark matter or dark energy for propulsion, though this remains entirely speculative and beyond current scientific understanding. The nature of these cosmic mysteries currently offers no known mechanism for interaction that could be exploited for thrust. It is a quiet, profound whisper of a future physics, a dream of tapping into the universe's deepest secrets for propulsion. This concept resides at the very frontier of our knowledge, a silent invitation to unravel the most fundamental aspects of the cosmos for an unhurried yet boundless journey. For an unhurried yet boundless journey. While the interstellar medium is incredibly sparse, its very vastness presents a tantalizing possibility: the interstellar medium as a resource. Although dilute, this cosmic expanse could potentially serve as a source of raw materials for future, highly advanced interstellar spacecraft. For theoretical concepts like the Bussard ramjet, the diffuse hydrogen and helium atoms scattered between stars could be gently scooped up and processed into fuel, eliminating. Even for other propulsion systems, the ability to extract and refine trace elements from the interstellar gas and dust, if the technology existed, could provide vital resources. Profound dream of cosmic self-sufficiency, transforming the seeming emptiness of space into a subtle, vast reservoir of potential. This patient, resourceful approach would allow humanity to truly live off the land of the cosmos, enabling unhurried, independent voyages across light years. For human crews, the emotional and ethical implications of certain missions are profound. The psychological impact of no-return missions would be immense. These are journeys designed as one-way trips, or where a return to Earth is practically impossible due to the vast distances and the immense timescales involved. Such a commitment would require extraordinary individuals, prepared to leave behind everything familiar, knowing they would never see their home planet again. The psychological burden of this irreversible decision, coupled with the isolation of deep space and the passage of centuries, poses unique challenges. It is a quiet, profound test of the human spirit, demanding an unparalleled sense of purpose and resilience. These missions raise deep ethical questions about the responsibility to those who embark on them, and the very definition of a home when one is adrift in the cosmic ocean. The decision to undertake such a journey would be a silent, momentous leap of faith into the vast, tranquil unknown. As interstellar missions grow in complexity and duration, the computational demands for navigation, data analysis, and system management will become astronomical. This is where the role of quantum computing in navigation and other critical functions could become indispensable. Quantum computers, leveraging the principles of quantum mechanics, possess the potential to perform calculations at speeds and scales far beyond classical computers. This unprecedented capability would allow for near instantaneous processing of vast datasets, real-time trajectory adjustments even for relativistic speeds, and the rapid analysis of complex scientific data from distant exoplanets. The quiet, elegant power of quantum mechanics could unlock new frontiers in cosmic exploration, making previously intractable calculations manageable. It is a subtle, yet profound technological leap that promises to revolutionize our ability to navigate and understand the universe, offering a gentle, powerful hand to guide our unhurried journeys through the intricate cosmic tapestry. As our probes venture further from our home star, they encounter a crucial landmark: the cosmic shoreline of the heliopause. This is the boundary where the sun's gentle, outward-flowing solar wind meets the thin, diffuse interstellar medium. It is often described poetically as a shoreline because it marks the point where the familiar influence of our sun gives way to the vast, open ocean of interstellar space. For our outbound probes, like the Voyagers, crossing this boundary was a momentous occasion, a quiet passage from the familiar into the truly unknown. The heliopause is a dynamic, invisible barrier, a landmark for our outbound probes, a testament to the sun's far-reaching yet finite embrace. It is a serene frontier, a subtle transition that signifies our initial gentle entry into the wider galaxy, a quiet, profound marker on humanity's patient journey towards other stars. For establishing new outposts of human life beyond Earth, the seed ship concept for colonization offers an elegant, if long-term, solution. A seed ship would be an uncrewed vessel carrying not adult humans, but rather genetic material, embryos, or even dormant cells, along with a sophisticated array of robots and artificial intelligence. Upon reaching a new, potentially habitable planet, the AI would then orchestrate the entire process of cultivating life. This could involve terraforming the planet, building necessary infrastructure, and eventually growing and raising new generations of humans from the carried genetic material. This method bypasses the immense challenges of supporting adult humans on a multi-century journey, relying instead on the resilience of genetic information and the capabilities of advanced AI. It is a quiet, patient act of cosmic gardening, a subtle, profound way to propagate life across the stars, gently entrusting the future of humanity to silent, robotic caretakers on a long, unhurried voyage. Despite the promise of advanced shielding, the challenge of long-term radiation exposure remains a significant health concern for human crews on interstellar missions. Interstellar space is permeated by high-energy cosmic rays and stellar radiation, which can penetrate even robust shielding over extended periods. The cumulative effect of this low-level radiation exposure over decades or centuries of interstellar travel could lead to increased risks of cancer, DNA damage, and other degenerative health issues. This subtle, pervasive threat demands innovative solutions, perhaps involving advanced active shielding technologies, or even a deeper understanding of human biology to enhance radiation resistance. It is a quiet, continuous battle against an unseen force, a delicate balance between exploration and preservation, ensuring the gentle health of our voyagers as they traverse the vast, tranquil, yet subtly hazardous cosmic ocean. As an alternative to the extreme measures of cryosleep, researchers are exploring the potential for hibernation instead of cryosleep for long-duration human spaceflight. Induced hibernation, or torpor, would involve slowing down a human body's metabolic rate to a significant degree, but not entirely halting it, as in cryosleep. This would reduce the need for food, water, and oxygen, and could potentially mitigate some of the negative effects of weightlessness. While still a significant scientific challenge, inducing a reversible medical torpor is seen as a more feasible and less extreme alternative, offering a more gentle transition in and out of a suspended state. It is a quiet, hopeful avenue of research, aiming to allow human crews to patiently sleep through vast stretches of their journey, preserving their health and resources without the profound uncertainties of full cryogenic preservation. This subtle biological adaptation could revolutionize the nature of long, unhurried human voyages. For launching massive payloads or even accelerating light sails to interstellar velocities from Earth, the mass driver for launching payloads offers a compelling alternative to traditional rockets. Mass drivers are electromagnetic accelerators that could use powerful magnetic fields to propel objects to incredibly high speeds along a long track, launching them into space without the need for chemical propellants. Imagine a colossal railgun on the surface of the Moon or in Earth orbit, gently accelerating cargo or even light sails to escape velocity or beyond. This method offers a cleaner, more efficient way to lift payloads, reducing reliance on expensive and pollution-heavy rocket launches. It is a quiet, powerful vision of future space infrastructure, transforming the act of launching into a smooth, electromagnetic push. The mass driver represents a patient, subtle re-engineering of our launch capabilities, providing a gentle, powerful impulse for our unhurried journey to the stars. The interstellar comet hypothesis proposes a fascinating scenario for the origin of life. This theory suggests that early life on Earth might not have originated solely on our planet, but could have been seeded by microorganisms transported across interstellar space on comets or asteroids. Imagine tiny, resilient microbes, encased in ice and rock, drifting silently through the cosmos for millions of years, eventually crashing onto a nascent Earth and sparking the genesis of life. This hypothesis implies that life might be more widespread in the universe, gently traveling between star systems on these cosmic vehicles. It is a quiet, profound contemplation of life's cosmic journey, suggesting a universe where biological material is patiently exchanged across vast distances, connecting disparate worlds in a subtle, elegant dance of cosmic biology. The interstellar comet paints a picture of life as a resilient traveler, patiently waiting for the right conditions to bloom. As humanity ventures further into the cosmos, our own exploratory artifacts will become historical relics. The cosmic archaeology of interstellar probes refers to the possibility that future civilizations, perhaps even alien ones, might encounter and study our interstellar probes, like Voyager 1 and 2, as artifacts of a long-past civilization's earliest attempts at interstellar travel. These hardy, silent messengers, drifting through the deep space, could one day be discovered and analyzed, offering insights into humanity's technological capabilities, scientific aspirations, and cultural values from billions of years ago. It is a quiet, profound thought that our distant descendants, or even other beings, might become cosmic archaeologists, patiently piecing together the story of our nascent steps into the galaxy. The voyages, in their unhurried journey, are silent time capsules, gently carrying humanity's legacy across the vast, tranquil expanse of the universe, waiting for a future discovery. For human missions destined to span millennia, the Generation Starship, as a micro-society, becomes not just a vessel, but a profound experiment in human endurance and adaptation. Such an immense starship would need to function as a fully self-contained micro-society, a miniature floating world with its own intricate systems of governance, evolving culture, and comprehensive educational frameworks. The delicate task would be to sustain human life, knowledge, and social cohesion across countless generations, ensuring that the initial purpose of the journey, reaching a distant star, is remembered and pursued by descendants far removed from the original voyagers. This requires careful planning for social structures that can adapt over centuries, educational systems to transmit accumulated wisdom, and cultural practices to maintain identity and purpose within the profound isolation of deep space. It is a quiet, continuous act of societal engineering, allowing humanity to patiently evolve within the serene confines of its cosmic arc, a testament to the enduring human spirit and its capacity for long-term, gentle self-organization in the face of cosmic timescales. The slow, graceful unfolding of this miniature civilization would be a profound journey in itself, a living, breathing testament to resilience. Pushing the very boundaries of theoretical propulsion, the photonic rocket concept proposes an elegant yet incredibly energy-intensive method for interstellar travel. These rockets would operate by using the momentum of emitted photons, tiny packets of light, for thrust. According to the laws of physics, even massless photons carry momentum, and by continuously ejecting a powerful beam of light, a spacecraft could generate a gentle but persistent forward push. Theoretically, this approach allows for incredibly high exhaust velocities, approaching the speed of light itself, leading to potentially swift travel times. However, the catch lies in the immense power sources required to generate such a continuous high-energy photon beam. The efficiency of converting energy into photons for thrust is relatively low, meaning a photonic rocket would require an astronomical amount of energy, far beyond current capabilities. It is a quiet, beautiful dream of harnessing pure light for motion, a testament to the elegance of fundamental physics, patiently awaiting the technological breakthroughs that could turn this ethereal concept into a tangible reality, allowing a vessel to ride a silent beam of light across the tranquil cosmic ocean. At the very frontiers of speculative physics lies the concept of a dark matter drive. This idea, purely theoretical and currently beyond any scientific understanding, imagines a propulsion system that could interact with dark matter for thrust. Approximately has, so far, completely eluded direct detection. Its nature remains one of the deepest enigmas in cosmology. Because dark matter does not interact with light or ordinary matter in any known way other than gravitationally, envisioning a dark matter drive that could harness or manipulate it for propulsion is currently impossible. there is. This concept serves as a quiet reminder of the vast gaps in our cosmic. It resides at the very edge of our scientific dreams, a profound whisper of possibilities that lie far beyond our current grasp, patiently awaiting a revolutionary understanding of the universe's most elusive component. Long before humanity contemplates journeys to distant stars, our initial probes charted the familiar pathways of our own solar system. The Voyager missions, launched in the 1970s, famously executed a grand tour of the outer solar system, using gravity assists from Jupiter, Saturn, Uranus, and Neptune to gain incredible velocity. This ingenious technique, where a spacecraft steals orbital energy from a massive planet, served as a crucial precursor, paving the way for understanding interstellar trajectories. The Grand Tour demonstrated the power of celestial mechanics and patient planning to achieve high speeds with minimal fuel. The data and experience gained from these unhurried, decades-long voyages provided invaluable insights into designing missions that could one day venture beyond our sun's influence. It was a quiet, deliberate exploration of our cosmic backyard, laying the foundational knowledge for the far more ambitious journeys to other stars, a testament to the elegant dance between spacecraft and planetary gravity, gently pushing the boundaries of our cosmic reach. For the preservation of life itself, beyond just humanity, the concept of an interstellar arc for biodiversity emerges as a profound and essential vision. Beyond carrying human embryos or genetic material, such an arc could be designed to carry a vast, comprehensive library of Earth's entire biodiversity. This would include genetic samples, cryogenically preserved seeds, spores, and even dormant microorganisms, representing a wide array of species from our home planet. The purpose would be to preserve this delicate biological heritage, safeguarding Earth's rich tapestry of life for a new home among the stars, should our own world ever face an existential threat. It is a quiet, immense act of stewardship, ensuring the continuity of life's intricate beauty across the vast, tranquil expanse of the cosmos. This ark would be a silent, floating repository of Earth's living wonders, patiently carrying the gentle spark of biological diversity to new, distant shores, a profound commitment to the future of all life. Stars, including our own sun, are constantly emitting a plasma wind of charged particles, gently flowing outwards into space. This stellar wind, composed primarily of electrons and protons, can be harnessed for propulsion or braking by advanced spacecraft. Magnetic sails, as discussed earlier, could potentially interact with this plasma wind from stars. By generating a powerful magnetic field, a spacecraft could create a kind of virtual sail that catches the momentum of these charged particles, either for propulsion, gaining a gentle, continuous push away from a star, or for braking, slowing down as it approaches a destination. This elegant interaction with the pervasive stellar outflow offers AI, similar in principle to how solar wind sails use photons. It is a quiet, subtle dance with the energetic breath of stars, allowing a vessel to patiently ride or resist the gentle cosmic currents, a testament to the ingenious ways we might one day interact with the universe's own flowing energies. To protect the most sensitive components of a high-speed interstellar spacecraft, engineers envision a probe shield concept. This would be a leading, sacrificial component of an interstellar spacecraft, positioned at the very front of the vessel. Its primary design purpose would be to absorb the relentless impacts from dust and micrometeoroids, which, at relativistic speeds, become incredibly energetic and destructive projectiles. The probe shield would gracefully endure this constant, subtle bombardment, slowly ablating or being gently eroded over the course of the journey, protecting the delicate scientific instruments, habitat modules, and propulsion systems behind it. It is a quiet, enduring act of protection, a testament to resilient design that anticipates the subtle hazards of the cosmic journey. This sacrificial layer ensures the integrity and longevity of the main craft, allowing it to patiently complete its mission of discovery, a silent guardian against the pervasive, tiny perils of the vast, tranquil interstellar void. Beyond merely traversing the void, the journey through interstellar space itself offers unique opportunities for scientific discovery. The interstellar medium, as a scientific laboratory, means that the journey itself becomes a primary mission objective. Rather than just being an empty pathway, the interstellar medium is a dynamic, albeit incredibly diffuse, environment containing gas, dust, cosmic rays, and magnetic fields. A probe's instruments can continuously study the composition and properties of this medium, providing new cosmic insights into the matter that exists between stars. This allows scientists to understand the conditions in which new stars form, how elements are distributed throughout the galaxy, and the nature of cosmic rays far from stellar influence. It is a quiet, continuous act of observation, transforming the vast, silent expanse into a rich source of knowledge. The journey itself, therefore, becomes a patient, ongoing experiment, gently revealing the subtle complexities of the space between the stars. To accurately plan and execute interstellar missions, precise knowledge of the distances to potential target star systems and exoplanets is absolutely crucial. This requires extending the cosmic distance ladder for exoplanet distances. The cosmic distance ladder is a series of interconnected methods used by astronomers to measure increasingly vast distances in the universe, typically applied to galaxies. For interstellar travel, this ladder must be refined and extended to precisely measure the distances to nearby exoplanets. This involves using techniques like stellar parallax for very nearby stars, and then potentially other methods to gauge distances to more remote exoplanet systems. Accurate measurements are essential for calculating travel times, fuel requirements, and orbital insertion trajectories. It is a quiet, meticulous process of cosmic cartography, ensuring that our patient journeys are guided by the most precise understanding of cosmic geometry, a testament to the elegant precision required for interstellar navigation. Ultimately, interstellar travel embodies a profound long now perspective. This concept recognizes that efforts begun today might only bear fruit for generations, or even millennia, far into the future. It requires a deep intergenerational commitment, where the initial planners and builders will never see the culmination of their work. This long now perspective challenges humanity to think beyond immediate gratification, fostering a patient, enduring vision for the future. It is a quiet, philosophical acknowledgement of cosmic timescales, where the legacy of one generation is gently carried forward by the next, ensuring the continuity of purpose across vast stretches of time. Interstellar travel thus becomes a testament to human foresight, resilience, and the capacity for profound, collective dreaming, a silent, unhurried commitment to a boundless future among the stars, a gentle unfolding of humanity's destiny across the tranquil expanse. And now, the vastness of the cosmos begins to gently fade behind your thoughts. You have drifted through 100 quiet wonders, from the dazzling brilliance of newborn stars to the silent shadows of ancient galaxies, from the intricate web of dark matter to the faint whispers of cosmic background light. You have traveled through starry nurseries, soared along luminous spiral arms, and glimpsed the heart of the universe glowing softly across unimaginable distances. You are part of this cosmic story. Not just an observer, but a participant woven into the fabric of stardust and time. The atoms in your body were forged in the fires of ancient stars. The air you breathe carries the legacy of distant explosions. Everything within you shares a lineage with the universe itself, born from the same primordial matter that now flows through galaxies and drifts in interstellar clouds. Tonight, as you rest, the cosmos continues its quiet unfolding. Stars are forming, light is traveling, and cosmic dances carry on in silent harmony. You are a small, warm presence within this vast, radiant sea, peacefully floating among the stars. Thank you for journeying through the cosmos tonight. I hope you sleep well and dream softly. Good night, softening into a peaceful, distant hum. Tonight, each one a shimmering facet of the universe's grand, unhurried story. From the dazzling brilliance of newborn stars, igniting in vibrant nebulae, to the silent shadows cast by ancient galaxies, patiently merging over eons, your mind has traversed incredible cosmic landscapes. We have journeyed through the intricate, unseen web of dark matter, the cosmic scaffolding that cradles clusters of galaxies, and listened to the faint, pervasive whispers of cosmic background light, the universe's oldest, most tranquil echo. You have soared along luminous spiral arms, where billions of stars patiently trace their paths, and glimpsed the serene, a beacon of primordial energy. This gentle exploration has taken you through starry nurseries, places where new suns are quietly born, and past the hushed, expansive voids, where galaxies are sparse, revealing the delicate balance of structure and emptiness that defines the cosmos. Every fact, every image, has been a soft brushstroke on the canvas of your imagination, painting a picture of a universe that is both immense and intimately connected. As your awareness settles, consider this profound truth. You are a fundamental part of this cosmic story. You are not just an observer, passively witnessing the universe's gentle unfolding, but a participant, intricately woven into the very fabric of stardust and time. The atoms that compose your body, every single one, were forged in the fiery hearts of ancient stars, stars that lived and died billions of years ago, patiently enriching the cosmos with the building blocks of life. The very air you breathe, the molecules that sustain you, carry the legacy of distant, majestic stellar explosions, scattering their precious elements across the galaxy. Everything within you, every cell, every thought, shares an unbreakable lineage with the universe itself. You are majestic galaxies, drifts in ethereal interstellar clouds, and forms the quiet, enduring planets that circle distant suns. This deep connection is a serene reminder of your place in the grand, unhurried dance of existence, a gentle embrace from the cosmos itself, affirming your belonging within its vast, tranquil expanse. Tonight, as you rest and your eyes grow heavy, the cosmos continues its quiet, patient unfolding. Far beyond our planet, new stars are forming, slowly gathering gas and dust under gravity's gentle hand, destined to shine for billions of years. Light, released from distant quasars and nascent galaxies, is still traveling, patiently crossing unimaginable gulfs of space, carrying ancient messages to future observers. Cosmic dances, the slow, elegant merging of galaxies, carry on in silent harmony, reshaping the grand architecture of the universe with grace and patience. Planets orbit their stars in rhythmic, predictable ballets, while moons gently caress their worlds. The cosmic web subtly stretches, guided by the unseen hand of dark energy, expanding the universe in a continuous, unhurried breath. These processes, vast and profound, occur with an exquisite calm, unperturbed by the fleeting moments of human time, a testament to the universe's enduring, placid nature. Of stars, peacefully floating, your consciousness gently tethered to the rhythm of the cosmos. Imagine yourself drifting softly through the quiet currents of the galaxy, a serene traveler amidst glowing nebulae and silent star fields. Let the immensity of what you have heard settle softly in your mind, like distant light on a calm, clear evening, bringing with it a deep sense of peace and belonging. The universe, in all its grandeur and complexity, is a place of profound tranquility, a silent, majestic canvas upon which all existence unfolds. You are embraced by this cosmic calm, held gently within its infinite, patient embrace, a cherished part of its unending story. Allow the quiet beauty of these cosmic truths to lull you into a state of deep relaxation, letting go of all worries, all thoughts, as you become one with the serene, unhurried rhythm of the universe. May your rest be profound and peaceful, a gentle drift into the tranquil depths of slumber, your mind filled with the quiet, elegant wonders of the stars. Good night.